Hello. In this video, we are going to explain the project named Author Context. This was part of the IIT project, uh, part of the host project in IIIT. So let's begin. So this is a project for the research community itself. So many a times, like, the research community wants to know where the different authors will be publishing the future work. So with thousands of research papers published every year, it would be really helpful for collaborators to know in which domain an author is likely to work. So in this project, we have taken the dataset from DBLP archives, where a large number of computer science papers were sampled and filtered, and we have used those tags to predict in which area the author is likely to publish a paper in the near future. So what exactly is a citation network? When an author collaborates with another author, so if we draw an edge between those two authors, then it forms an edge of a citation network. So in this way, as we can see in this picture, various authors have collaborated over the years, and this has led to the formation of the citation network. So in this network, the author name and as well as the year in which the author collaborated with his or her colleague has been shown. So next we move on to the data sets. There was a DBLP paper dump dataset which had more than 2.2 million papers. These papers were covered over like several domains, which included computer science and other disciplines of science, as well as like maths, physics, and others. So the dataset containing the research papers and the incomplete author names were referred from this reference paper, the link of which has been given. So these contain the author names which were incomplete. And for predicting the authors and their tags, we need complete author names. So first we needed to match these 2.2 million papers along with the authors in the incomplete author names dataset. So another dataset which we used was the dataset which contained the paper names, authors, and their respective tags. So DBLP dataset contains papers from all domains, as I said earlier. So we matched it with the paper titles and IP address to fetch each computer science paper. We recorded 4,16,000 matches. Next, we extracted the tags of the papers from the tag paper dataset in DBLP. We found 295,000 unique authors from this dataset. In order to calculate the tag associated with each author, we calculated all the publications of the authors in every field of computer science and tagged the author with maximum publications in the subfield. Once we had those unique 295,000 author names, we had to further match it along with the tags which were available in third DBLP dataset, as mentioned earlier. And from there we got 216,000 matches. So this was our final data set. So here after the pre-processing had been done, and like after the first pre-processing part where we matched it with the paper titles and IP addresses, we got this file. So as you can see that the first column represents the paper name which has been pre-processed in order to increase the number of matches. The second column lists the author names which published the paper. The third column is the RNet ID. We had downloaded the dataset from rnetminer.org. So the third column represents the RNet ID, and the fourth column is the IP, which can be used to fetch the contents of the whole paper. So since we have around 216,000 author names, it is not possible to load all the author names in the RAM. This is because we used Lua for Lua API for programming the neural network in order to learn it. So the Lua API has a limit of 2 GB. So which is why we couldn't load the whole thing into the RAM. So we had to use a Lightning memory map database, which is also known as LMDB, to store all the 216,000 entries. So it's a high-performance embedded transactional database which stores the data in the form of key-value pairs. So our next task was to classify the authors, and for that we needed numerical vector representation for each author. So here we have used word2vec. So since we have the word in our case is author names, so we call it author2vec. And that was mentioned in the research paper which was cited earlier by us. So this method gives us a weight vector for each author. So I'll be explaining it in the later slides how this works. So it gives us a weight vector for each author. The length of the weight vector is predefined. So we can enter how much size of each vector we want. Suppose we enter 50, so that means there will be 50 floating point numbers or weights which will represent an author. These can be considered as feature vectors. In order to train these, we used skip-gram model with negative sampling, which is a technique used in word2vec. So this is a general model of word2vec. The first one is CBOW, in which various words are taken as input and we are trying to predict the missing word. And the skip-gram model is quite the opposite, in which a word is present and we are trying to predict all the other words on the basis of that. So as I said earlier, in our case the word2vec is author, so we call it as author2vec. So it contains two flavors, the continuous backup of words and skip-gram. Algorithmically, these models are similar, except that CBOW predicts target words, and as mentioned earlier, they're just exactly the opposite. After learning the word weight vectors, this is what we got. So the index number at the left-hand side of the screen is the author ID. So for author 1, we are getting these weight vectors, this weight vector containing these weight values learned, and the author IDs can be listed on the left-hand side of the screen. For training the classifier, we have used several parameters for the neural network. So the learning rate is 0.001, which is basically trial and error. The embedding size is 100. So we get 100 weight values to represent one author. Negative sampling. Now we need to create the negative sampling file. So in order to do that, we need to know what exactly negative sampling is, and I've explained it in the later slides. So we are using 50 epochs. Naturally, if higher number of epochs are used, then we will get better accuracy since the training error will reduce. And BC criterion is used, and the window size is 1, which means we are just considering the next word. So in negative sampling, there needs to be a window size, which means for a particular word, how many words nearer to it are we considering. So for example, if the window size is 2, and if I have a word x, so I will consider only x minus 1 and x plus 1 word. So in the skip-gram with negative sampling, we need the one thing which we need to get clear is what is negative sampling. So what exactly is negative sampling? So what it means is, in our case, say for author 1 has collaborated with author 2 and 3 and not collaborated with authors 5 and 6. So this means that author 5 will be a negative sample for author 1. So in this way, for each author we have, for each collaboration rather, we have used 3 negative samples. So it has been further explained here what exactly negative sampling and skip-gram is. So for a vector W, for each word W in a vocabulary PW, each such vector has d latent dimensions. This is an example of a negative sample file. In the first line, we can see 8644 is there. The first word is the one the author has collaborated with. So the author with an ID of 8644 has collaborated with an author of ID 1831 and not collaborated with an author of ID 2338. So for each collaboration, that is, for each 8644 has collaborated with 1831, we have used 3 negative samples as illustrated by the top 3 examples in this slide. Next, 8713 has collaborated with 1898. So each time we use a negative samples, and we have used 3 negative samples for them. Next we want the author tags. So the dataset which we had obtained, like we had 2,95,000 authors, unique authors. So from there we matched it with 2,16,000 authors. So in order to calculate the tags, what we have done is we have considered all the publications of each author in the various domains that are available to us. And then we have kept a count of how many publications in each domain an author has. And then we have used the maximum count as the author tag. So there were 25 such cases in our example, in our data set rather. So the classes were artificial intelligence, computational biology, etc. We got 24 unique tags, 25. So we indexed them from 0 to 24. Here is an example. For example, at the bottom of the screen, A. Adams has a tag of artificial intelligence. The final step is the classification. So here we chose to use support vector machine to learn the classification boundaries. SVM, as we all know, is effective in high dimensional spaces. So we had an embedding size of 100. So it's effective in cases where number of dimensions is greater than the number of samples. Although this is not true in our case, but we got good results using SVM. The kernel function which we used was RDF kernel. We have listed the results in the next slide. So there are two types of SVM classifiers mainly. So one is 1 versus 1, which means like for each pair it learns a classification boundary. So for example, if I have 4 classes, I will have 4 C2, that is equal to 6 classifiers learned. And in case of 1 versus all, it means for 4 classes I will learn 4 classifiers. So each one I will compare with all of the rest. So these are the accuracies which have been mentioned as a percentage. So thank you.